remain in the world of hydrology, and we are in the subsurface, dealing with groundwater. And this is going to be our second groundwater lecture. Again, textbook 11.6, also the internet and Wikipedia. Today is all about geography. But remember, groundwater is invisible, and so these are invisible geographies. That's going to be the main topic today. Geographies of the invisible. We'll have one master sketch here at the top, and then I'll label it and add different terminologies for you to add to your vocabulary. So here is our landscape, and on this landscape we'll put a little creek in it. That'll help us with the water table. The water table will intersect with that creek, and it will follow the topography up, intersect with the creek, follow the topography up, follow the topography back down. Let's see, what other things can we add to this drawing? All right, we could add some plants just to demonstrate we're at near the surface here. Okay, this is just for our create. You could draw cities and people, animals. I don't have that ability right now, but I do have the ability to give you what I've just given you. All right, so this area above the water table, this will be number 1. This is called the vadose zone. Vadose zone. And the key to the vadose zone is that it is above the water table. It is not saturated. This is the world of percolation. It's dry or moist, depending on the drought level, but it is not saturated. The pore space is not filled with water. Number 2, down here. This is the saturated zone. Saturated zone. This is now below the water table. If the porosity and pore space are right in this material, we call this area an aquifer. If the pore space and permeability are bad, they do not allow water to flow, we call it an aquitard. So this is rock or sediment in the saturated zone below the water table, but the aquifer has good porosity and permeability. I'll put K for hydraulic conductivity for that. And an aquitard is one where it does not allow water to flow through it. So we would say tight or poor porosity. So let's just say no porosity or permeability. And I'm giving goods and bads associated to this because I'm thinking of this from the farmer's perspective, from the hydrogeologist perspective, where typically we are searching for aquifers because we need water for some use or application. Of course, a rock is neither good nor bad. Aquitards have their utility in different environments, but typically we assume aquifer for good. Okay, so this is our vadose zone, our saturated zone. I suppose we should label the water table now. Let's go number 3, water table. And the key to water table, it's the contact between the not saturated and the saturated zone. So this is 3. And so it is a surface. And I guess it's not imaginary, it is there, but it is a contact line that defines these 2 different realms between saturated and unsaturated zones. A couple rules for the water table about how the water table behaves. One, it follows topography. So we'll go 3A and 3. Why would I do B first? That doesn't make sense. 3A and 3B. So the rule 3A is that it follows topography, follows topo. And so when a hill goes up, the water table goes up. So maybe we put like 3B here. See how this is the highest topography and it's also the highest part of the water table. And then the second rule is 3A. Wait a minute. I did it. Why did I do that again? 3 follows topography. Follows topography. That's 3B. I drew an A right here where it meets the stream. 3A. That's bad teaching. What did I want to say? Connects to surface water. Connects to surface water. Anytime there's a lake, a pond, or a river, a stream, you know where the water table is because it's at the edge of that thing. Okay, so Those are three very important things to define with respect to this geography of the invisible. There's a few more things I would like to define. I want to define for you a spring. I want to define for you a well. And I also want to, oh boy, the potentiometric surface and artesian springs. We're going to need to use some textbook pictures for some of those. All right, so let's do, since we lost the picture, here we go, let's do another picture. All right, here is our next picture. What do we have? We've got our creek, and we can demonstrate that we're near the surface of the earth by putting in some plants. And so for what is a spring and what is a well? Well, a spring is any place where the water table intersects land surface. And what is a well? A well is a hole that penetrates down into, the water table. It's a man-made hole. So what we need to do in order to draw this, we need to put in our water table. And so I'm going to draw a situation here where the water table is higher than the actual body of water. And so here, this line right here is going to be the water table. And so the place where the spring pours forth from the ground is right here. Because this is the point where the water table intersects the land surface. And because maybe we're in an area with significant drought, we haven't filled up the entire valley with water because there's not enough flow down into this creek. A well, we can add that. Here's our well, and it drills down. And so we have a well with water in it. This would be the area with the water. Okay, those are two definitions. Oh, well, we're building a nice lexicon on groundwater vocabulary. Here's our next picture. This is something I couldn't describe with my own drawings. So I want to define for you something called the potentiometric surface. And here's the word potentiometric surface. If you need more on this, go to the textbook, go to Wikipedia. Potentiometric surface. So this is in a pressurized system. This is where the water table would be if the water table were allowed to act the way it wanted to. But it's been blocked by some kind of geology. And I'm going to use this picture to show that. So I do want you to say that in a system with a potentiometric surface, we have some kind of pressurized groundwater system where geology is blocking the ability for the water to kind of equilibrate in the way it wants to. Geology is blocking the system. That would be another phrase to use. Maybe we could also say it's the location where the water table would be if it could. Where the water table would be. So now let's look at this picture here on the side. We have a situation. All right, let's just unpack this. We have a situation with an aquifer. Here's our aquifer. But notice that aquifer is stuck between an aquitard. This is our aquitard, and here is another aquitard. Maybe you can't tell that from the picture, but this pattern is a pattern for shale, and it doesn't allow anything to flow through. So when rain falls in these mountain highlands, it fills up the aquifer, and it gets trapped down here with the slope of the rocks. And so the water table would like to be at this line. And notice how this line is above the actual surface of the earth. And so if we were to puncture a hole down into this aquifer that's been pressurized, we'd actually get a well that like erupts water out above just the land surface. It's a gusher. And that's the last definition I wanted to put in is artesian well. Sometimes this is called an artesian spring, and it's just a place where we are gushing it's a gusher where the water is actually pressurized and pushes out. Pressurized water escapes. These are pretty cool to see, but they're also quite rare to see. Again, look it up on the internet, look it up in the textbook if you need a little more. That's probably the most complicated word and concept we have in this section. All right, now to finish off this lecture, I want to talk about problems with groundwater use. Because we are drilling wells and we're using about 30% of human use is from groundwater, we have some environments, some geographies where we're pumping too much groundwater out at a non-sustainable level. So problems from overuse. And there's a number of them, but there's 3 big ones that you should learn about at this level. And the first is called a cone of depression. This is a drawdown, like you're sucking on a straw at the bottom of your slushy. So here is our land surface, and we have 2 wells. And farmer A and farmer B are pulling on these wells, and they're dropping down the amount of water that's available in the reservoir. And what will end up happening sometime is that the water table will drop to a level where one well now becomes dry. All right, so this well is dry, and this well has been overpumped. By overpumping, we have this drawdown. So what this would have been the level, and so it's this area right here we'll say is drawdown from overpumping. Draw down. Officially in the notes, we're going to write down the definition as water table locally decreases from overpumping. Water table locally decreases from overpumping. And there are some areas where that word locally isn't even appropriate anymore. The whole regional groundwater has been depressed by overpumping from that aquifer. All right, number 2 is subsidence. Subsidence is land that is shrinking or going down. We could say land collapse or land sinking. And it's also from overpumping. So we could say overpumping removes water from porosity, and by removing it, the grains are all able to collapse together. So that allows collapse. And it's collapse at the sand grain scale. But if you collapse enough sand grains, you'll collapse the whole landscape. Let me show it to you in this picture in 2 different ways. One of the more famous places in the world for this is in California. And so in this region, it's a big farming region in Central California. Here's a map of the amount of subsidence over a period of around 50 years. And look at these colors. They're in this kind of range. That's maybe 10, 20 feet worth of subsidence. So here's a cool picture with the dog. This used to be land level, but there's been all this subsidence because of groundwater removal, allowing grains to compact closer and closer. The third and final problem from overuse is saltwater incursion. And this is due to using groundwater in environments near the ocean. Cities like Miami and Cairo are experiencing significant saltwater incursion. And the definition we'll put down first, this is where we are removing freshwater removal from an aquifer by overpumping allows saltwater to fill aquifer. It's a little bit tricky to draw this. Here we'll do our best. Here is our land and ocean. We're gonna have here's ocean. And now getting this drawn right is the key. There's going to be saltwater aquifer over here, and there's also going to be freshwater aquifer. And initially, let's see, how do we say this? There is a contact between salt and fresh water. So there's here over here it's fresh, and maybe I can draw it in like this. So here would be the contact between salt and fresh water in green. All right, that's the actual water table itself. And if we drill a well in and we start pumping, we're going to create a cone of depression. I'm going to do this in a different color now. Bear with me. So let's go red. So after over pumping, our fresh water will look something like this. It's going to have that cone of depression. But what's important is that the contact between the salt water and the fresh water moves, and it'll actually do something like this. And so now this well is pumping salt and is no longer useful for the city. That's the concept of saltwater incursion.